All right, everybody. Welcome into your ME 491 Senior Design Seminar. On to week 6, getting near the end in your deadlines coming up for the class. Just want to tell you a couple reminders quickly about deadlines that we do have coming up for the class. Just a reminder that your either interim report, if you're continuing on for the third quarter, or your final design report is due in PDF form to me Monday of week 11, which is February 22nd. So you and your advisors should have some pretty good handle on that at that point, know what that document should look like probably at this point. So if not, make sure you have some conversations with your advisors about that. Secondly, we will have oral presentations of the design the Friday of finals week, which is week 11. We're in the process of putting the schedule together for that right now. And you should be getting a question from your advisor about if you have any conflicts on the Friday of finals week for your presentation schedule. I've heard back from a couple of you already about conflicts in times for possible presentations on that Friday, which would be February 26th. So please make sure to send me some of those conflicts or have your advisor relay those conflicts to me if you have any conflicts on Friday, February 26th for your oral presentations. Okay, so with that out of the way, I want to introduce or talk about our speaker today. So the speaker today, he's a close friend of mine I've known for quite a while. It's Dr. John Springmann. Before I sort of fully introduce him, I want to talk a little bit about how his seminar and his presentation fits in a bit with your seminars that we've had for 491 so far. And really, I think this comes down to 3 reasons. Like, number one is John just works on really cool stuff. Okay, so you'll hear in his presentation, he's worked on the design of satellites that have gone into space and just really cool, interesting stuff. I don't want to give too much away right now, but reason number one why I want him here is he just works on cool stuff. Reason number 2, I want to invite John to the talk today is because he's always sort of had a focus on economics with his work. He'll probably talk about this a little bit, but the title of his dissertation was actually, I have it here, Satellite Attitude Determination with Low-Cost Sensors. And so half of the title of his dissertation here relates to economics, and I think that is kind of a nice thing because it fits in with sort of what we've discussed over the last couple of months with your ABET accreditation for engineering and what is expected of you coming out as an engineer in the things that you know. So, the last couple of seminars have dealt with very specific topics related to design, and those topics have been kind of driven by these ABET accreditation standards, where we're trying to get you at least informed or have an ability to apply engineering to design to produce solutions that meet a variety of needs, including those related to global, cultural, social, environmental, and economic factors. Now, we had Dr. Severe come in here and talk about cultural factors with Engineers Without Borders. We had Dr. Cole come in last week and talk about his design of environmentally friendly surfboards. So that leans on the environmental side. And now I think it's really nice to have John today to kind of talk about some of the economic sides of design and how that sort of fits into design as kind of a holistic metric. So that's kind of where he fits in a little bit today with his talk. And reason number 3 why I want to invite John today is because his path and his career path has generally followed a bit of a non-traditional path, I guess you could say. He started out working for a company after he got his doctorate and then went on to sort of become a full-time consultant and has been doing that now for quite some time. And so it's a little bit non-traditional. I wanted to expose you maybe to a sort of different type of career path that if you hone some particular skills, you might be interested in pursuing in the same way that John has. So, okay, without further ado, let me give John a full introduction here, and then we'll give him the floor to speak. So I want to introduce a longtime friend of mine, John Springmann. We actually both born and raised in Racine, Wisconsin, right down the road. So I've known John a long time. John got his bachelor's degree in engineering mechanics from the University of Wisconsin, right down the road here in 2009. Right, 2009, right, John?
Yep.
Yeah, 2009. And then he went on to get his doctorate in aerospace engineering at the University of Michigan. After that, he's sort of worked for a short time at a small satellite design firm, I think is kind of the general sense, and has now gone on to become sort of a full-time consultant for his job, where he's consulting on building small satellites and helping design their missions, which is really awesome. So without further ado, I think I will relinquish control to John here and let you sort of explain some of what you do, and take it away, John.
Sounds good. Thanks, Kevin, and morning, everyone. I'm going to try to share some slides here real quick. Hopefully that's coming through okay.
Yep, see it just fine.
Cool. Yeah, just a quick intro for this morning. I'm going to give a quick background of, I guess, who I am and a bit more of my background, and then talk through kind of two specific examples of where cost has come into play in some of my work. One of the examples is some of the my grad school work that Kevin showed you the title of there. And then a second example with Constellation Design for small spacecraft, and then just kind of wrap it up with a couple of general kind of takeaways or lessons learned. So a quick background on myself, like Kevin mentioned, I have my bachelor's from the University of Wisconsin, and then went right to grad school over at the University of Michigan in Ann Arbor. And my focus there was aerospace engineering. I guess more specific focus was spacecraft design and spacecraft flight dynamics and control. After that, I went to a startup company out in Seattle. I'm still in Seattle now. The company was called Black Sky Global. So if you're familiar with the kind of new space industry at all, there's a whole wave of private capital coming into the industry, and tons of these startup companies that are trying to build small satellites commercially for various applications, really around data collection. So Black Sky is one of those startups. I was there for about 4.5 years. I have a couple pictures of their spacecraft, which I'll show. And then since then, I've been doing some independent consulting. I've spent a lot of my time with another space company called Rocket Lab. And kind of in these different roles, it's been various leadership, kind of engineering management, system engineering, program management, kind of where technical meets actual program execution. You have to actually build something tangibly, quickly, on schedule, on a budget, things like that. So a few pictures just to get us kicked off, and a little orientation of some of the spacecraft. So RAX 1 and RAX 2 are shown here. These are spacecraft that I worked on when I was a grad student at University of Michigan. So they were kind of student projects that were done in collaboration with another organization called SRI International. So these are 3U CubeSats, they're called, about the size of a loaf of bread, 30 centimeters tall and 10 by 10 width. So these satellites were developed to study space weather. Don't want to get into the details too much, but they have a radar receiver in them, and we were transmitting radar from the ground through Earth's atmosphere. And when it gets to the ionosphere and these kind of features of space weather, it'll actually scatter. The signals will scatter off the ionosphere, and then our satellite was flying overhead, and it received those signals. So this was kind of my first exposure to hands-on spacecraft. I started working on a specific subsystem, the attitude determination and control subsystem. And then we got a couple of years later to the second spacecraft. I was kind of program manager of the program. These are a couple of pictures of the Black Sky satellites. So like I said, Black Sky Global is one of the companies that I've spent a good chunk of my career with so far. Black Sky is developing small remote sensing satellites, imaging satellites, specifically in the visible band. So there's two of the satellites I've shown here to the left, with all the nice surface coatings on them. These are about 50 kilograms, so kind of the size of a dorm fridge. In general, just to orient you a little bit, the cylinder here on the top, that's the telescope. It's about 25 centimeters in diameter. You point that at the Earth, and it can take pictures that are about 1 meter resolution. So each pixel is about 1 meter. Then the bottom of the spacecraft here, which you can't see the insides of, that's all the avionics and electronics. So power, communications, flight computer, that's all in there. And then here's a picture. So about 5 of those spacecraft have launched so far. They're still launching. They want to get to a constellation of spacecraft to provide really frequent imaging of any place on the Earth. This picture on the right is kind of.
What do you mean? What do you mean by a constellation? Can you just explain that quickly?
Oh yes, by constellation I just mean large number of satellites or multiple satellites. So not just one. And then their orbits are designed such that, I mean, it's not like formation flying, but it's just that you kind of understand their orbits relative to each other to kind of understand how they'll be able to complement each other. And the picture on the right is just kind of a fun one. This is one of the specific satellites, Global 4. That's actually a picture from the rocket. So once it's in space, it gets deployed or just kind of kicked off the rocket. That's
cool.
So yeah, that's Global 4 in space.
So that's not a rendering. That's the actual satellite.
That's the actual satellite. Yeah.
Yeah.
And it looks cool. looks a little grainy just because of the it's like a cell phone camera on the launch vehicle, basically.
That satellite can take pictures with 1 meter resolution, but the thing taking a picture of that satellite is not so great.
That's right. So here's just a sample picture from the satellites. Probably doesn't do it justice. I just grabbed this one out of the public domain on the internet. So again, probably a little grainy, but yeah, the whole push with Black Sky and a lot of these companies are what people are calling activity-based intelligence and kind of change detection. So if you take pictures of locations frequently, you can really derive a lot of insights of what's happening. And for small countries, you can actually drive their economic output essentially by looking at things like how many ships are in their ports, how many trucks are in their factories, what's the activity in their mines, things like that. So it's pretty crazy. There's a lot of cool articles out about it. Then kind of the third project I want to chat about, or just intro a little bit, is this company called Rocket Lab. Rocket Lab is a joint US-New Zealand company. They're probably most known for their launch vehicles. They build a rocket called the Electron, but they've recently started building spacecraft as well. So I got their spacecraft program started. I was kind of hired as a consultant early on to kind of scope and build their program. And they've launched just one demonstration satellite so far. It's really just to show the world, hey, we can build satellites too. And now they have a number of commercial contracts, including some deep space stuff. They're going to the moon and some other locations. But anyways, on the left is kind of a picture of the satellite. It looks maybe a little funky because it's actually also the third stage of their rocket. So it's kind of a 2-in-1 vehicle where it has an integral part of the launch vehicle. And then once it's done with its kind of primary purpose of launching spacecraft, it can continue on its own in orbit and continue to operate as a satellite. So the picture on the right is a picture from its camera. Again, not super high resolution, but super satisfying. So obviously the Earth there with the sun coming over the horizon, that was taken back in November. So now into a bit more detail, I just wanted to give kind of, like I said, 2 examples of how cost comes into play. One is I want to give an example from spacecraft attitude estimation. So this was a topic of my graduate school work. So a quick orientation on what is attitude. So qualitatively, it just means orientation or how the satellite is pointed. Let's see. So if you need to point your solar panels at the sun, if you're taking pictures of the Earth, you need to point that telescope down and have it very stable. If you're doing telescopes like the Hubble, looking at galaxies and things like that, it's kind of the opposite, pointed out to space. More quantitatively, attitude is the proper orthogonal rotation matrix that relates or defines the coordinate frame of the body frame. So some kind of coordinate system that's fixed to the satellite. Defines the orientation of that relative to some other inertial reference frame. So if you've taken courses on like rigid body dynamics, you've probably learned a lot about rotation matrices. So how do you actually figure it out? Well, in general, it's a bunch of sensors and also some very complex algorithms. so there's various classes of sensors. So the highest accuracy method is through star sensing. So you will actually fly cameras that take pictures of the stars, figure out where the centroids are of the stars, the middle points of the stars, and then figure out where on a star catalog or star map you're looking, and you can kind of back out the orientation of the spacecraft. Actually, back up to these Black Sky satellites, these 2 things hanging off. I don't know if you can see my mouse, but the little 2 conical things hanging off. These are actually the 2 star cameras.
Oh, cool.
So those are the primary attitude estimation sensors. You can use magnetic sensors, so sensing Earth's magnetic field, very much like a compass. So there's models of the direction and strengths of Earth's magnetic field. So you can, if you measure that on board, you can then kind of do a correlation or try to figure out again how you're oriented in the field. Same thing with sun sensors, figure out where the sun is, and then based on your position and time, you know where the sun should be, and therefore that gets you a data point. Rate gyroscopes, those are, oh, typo there, rage gyroscope. Sorry, it's supposed to say rate gyroscope. So those are sensors that measure angular velocity. So they don't give you attitude directly, but you can combine them with directional sensors to kind of smooth out your attitude and help figure things out. In general, all the sensors, kind of regardless of sensor type, are all corrupted by uncertainties and various error sources. And the algorithms as well. So algorithms will typically kind of merge a raw sensor measurement with a model of the system. You know, even if something as simple as like Euler's angles or Euler's equations that govern rigid body dynamics. You know, there's imperfections in the inertia. What's the inertia? What are the forces and torques that are acting on it? Things like that. So how do you figure all this out? It comes down to some pretty robust and statistically proper methods. But in general, this is an example where cost comes into play. Like a high-performing system is going to be very expensive, both at the component level and the system level. And then lower-performing systems may be cheaper, but you know, how do you know what to use? So just a quick spectrum on the left is a kind of a bit more of a classic star tracker. This one specific example is 2.5 kilograms and takes 8 watts of power. And in space, kind of mass and power is money. On the right there is a magnetic sensor. So that's one that we used on those CubeSats I showed. It's a very simple, on a chip, 3-axis magnetometer. It consumes about 1.5 milliwatts. So your overall system design is going to dictate which type of these sensors you need to use. But the thrust of a lot of my research was on how do you make the super cheap sensors, like on the right, work very effectively and high performing. So cost, in this case, it's going to be kind of hardware selection, right? What sensor are you buying initially? Ground-based sensor calibration and characterization. So what I want to get at here is that it's not just like the piece of hardware that costs money. You actually need to test it. And to test it, you need time, you need software, you need lab equipment, potentially some very specialized facilities, things like that. Then you've got to actually develop the algorithms to process the sensor data. Again, can be lots of time, especially if it's something new, as opposed to something that exists already. And then number 4, they're ground-based calibration and characterization. So there is the sensor itself. So that little chip, you know, you can get a development board or something very simple to actually test that chip. But then ultimately, it's going to get integrated into a kind of real satellite subsystem, which will get integrated into a satellite. And you know, these are directional sensors. So I'll take misalignment as an example. Like, how do you know how it's aligned in the vehicle? And when you start soldering it to a board and then bolting that board to something else, you know, what's even your reference point? And you can get these errors that stack up. So you need to figure out ways to back out those errors, or that's one aspect of sensor calibration, without driving a ton of cost, right? If you buy a $10 chip and then it ends up costing, you know, $1 million to go to a facility and calibrate it, then you know, not a great benefit. So what I developed in grad school is on-orbit sensor calibration. So you don't have to do any thorough calibration of the sensor pre-flight. You can actually just launch it and then use its measurements to calibrate itself. And I'm not going to go into the details too much of the methods. You can read the dissertation.
It's a thriller, I tell you, a thriller.
What we were able to show is that with kind of a couple $100 of hardware, we're using magnetometers. So this is that same chip that I showed earlier, but now it's mounted on a bit larger board. So this is the overall kind of attitude determination and control hardware module that was in that CubeSat I showed. There's a little chip there. And we're also using super simple sun sensors, or just photodiodes. So they basically have a voltage or a current output that scales as a function of the light intensity, and you can back out the angle to the sun if you have multiple of these sensors. And we're able to, get pretty good performance, so less than a degree of accuracy per axis with the super simple hardware set. So it's really enabling for these kind of class of missions where they're relatively cheap, fast development, things like that. And at this aspect is a bit of a, what I'd argue is kind of a component level or certainly a subsystem level thing. So this is just one aspect of one subsystem. So if you can try to find these savings in your technical development across everything, right? This is pointing, what about power? What about communications? Things like that. It can really stack up. And that's how the community is getting to relatively low cost satellites these days. You can put some pretty killer capability up for low millions of dollars. So the second example I want to give is much higher level, kind of system level constellation design. So we talked about constellations a bit earlier, so it's mini satellites typically. There's an example rendering on the left where these would be all the orbits, and then the little kind of cones with the circles pointing at the Earth, those are the kind of field of regard of the satellites, or what they can see, at a given point in time. So they're all going through the orbits around the Earth. Now on the right is a map of ground station locations from an example company called KSAT. So for spacecraft communications, you have to downlink your data through communications. So the black sky example I showed, it's taking those pictures. The pictures are getting stored on board on some onboard memory, and then when you have visible line of sight to a receiving station on the ground, you transmit all that data to the ground. And typically with traditional communications links, you can only transmit the data if you have line of sight to the ground station. All right, so you've got transmitters on the spacecraft, receivers on the ground, lots of satellites, lots of ground stations. How do you optimize the cost or the performance of communications? So satellites, if you want to have lots of them, the very, very, very rough cost is going to be the cost of the satellite plus the cost of the launch. Times the number of spacecraft. So Black Sky, for example, has about, like I said, 5 or 6 satellites today. The original goal was to launch up to 60 spacecraft. So each individual unit cost, is important. You're going to multiply it by 60. Now the ground stations, if I go back to this map, it's really nice to have a lot of ground stations, right? Because since the satellites are going around in orbit around the Earth and basically rotating, the more ground stations you have, the more frequent opportunities you have to downlink the data. So you can get a lot more data down, or you can get it more often, kind of depending on what you want to do. So again, ground stations cost of a single one times the number of them, while your total cost is the satellites plus the ground stations, right? So in a technical example here with the communication system is power. So data throughput generally is proportional to kind of how much power you're putting through. And if you're transmitting with a high amount of power, then you can receive it with a simple antenna. Whereas if you're transmitting with a low amount of power, you might need an expensive antenna. So you can kind of put the cost on the satellite or on the ground. So quick examples, these are some more CubeSats up on the left here. These copper things are what's called patch antennas. So pretty simple, just kind of solder them on. Whereas on the right, this is just a cartoon of a NASA TDRS satellite, which is a kind of a communications relay that NASA uses. And you can see these are like pretty traditional parabolic antennas, which are quite large. And really size is cost when it comes to spacecraft. Somewhere on the ground, I think DirecTV may go out of business soon, but DirecTV satellites are obviously quite small, right? They have to be small such that you can put them on people's homes. Whereas this is a NASA receiving station. It's kind of fun. Reminds me of one of the Star Wars episodes where they're in the jungle there. But this is real. This is outside of Fairbanks.
Yeah, they're protected by the Ewoks.
That's right. So you can imagine like these systems on the right are approaching kind of millions, if not billions. And so how do you optimize cost? How do you minimize your costs? So again, the example here is where to put the power. So if you want to put more power on the spacecraft, you could get away with this DirecTV antenna, for example. But more power on the spacecraft means more solar panels. All right, so that means, and more power in general is more power dissipation. So electronics will have, finite efficiencies where not all the power is actually used. A lot of it turns into heat. And on spacecraft, that's tricky because there's no convection. So how do you get rid of that heat? So there's more thermal control. In general, both of those lead to more mass. If there's more mass, then it's going to cost more to launch it. You need a larger rocket. So really this gets at kind of a discipline that's sometimes called systems engineering, to look at the system holistically, right? If you're going to design a communication system, for example, you can't just look at the design of that little transmitter on the spacecraft. You can, but it's a very narrow view. And if you try to just look at that subsystem without looking at the whole thing, like, hey, how do the performance requirements flow down from what the system needs to do? And it's not just performance, it's cost. So again, BlockSky is an example. We had targets from a business perspective of the total cost of those ground stations I mentioned and of all the satellites. So how do you actually build both of those together and minimize your cost? So to kind of wrap things up or to summarize, I'm sure a lot of your courses have been technical. Most engineering courses are largely technical, but really it comes down to a lot more than just technical. And any complex system, you're always trading cost, schedule, and risk. Generally, you can't really minimize all three. You can kind of pick the one or two priorities. You're either going to eat some more cost in exchange for a really condensed schedule and maybe a really low risk program, or conversely, you can kind of flip them around. And when you're designing complex systems, like spacecraft or constellations or aircraft, autonomous cars, anything that has this pretty complex system of systems approach, it can just get exacerbated. So there's the technical aspects, there's the cost aspects. Cost you can break out to what's called recurring and non-recurring. So recurring would be like, hey, if you're going to build a thing multiple times, what are just like the fixed costs to build it over and over? Whereas non-recurring is the development costs that would go towards that product that you don't have to pay multiple times, but you pay really just once. Schedule, risks, and again, risks are, you can have technical risks like, hey, that angular accuracy might be 1.5 degrees rather than 1 degree. Is that okay? If it's not, then you're going to have to spend more money and time to actually fix that. At the same time, there's cost and schedule risks, right? If you're buying components, your vendors can fall behind, ship things late, things just take longer than expected. And then outside of academia, in the commercial world, time and labor can be the most costly things. So, if you're going to take a longer time to develop a program, it's just going to be directly proportional to higher costs.
I like how you said outside academia, because we all know grad student labor is free.
Relatively low cost.
Relatively low cost, exactly.
So, and there's things like maintenance, usability. So yeah, just what I want to highlight is that it's, you can get into these really niche design elements, but you really need to keep that system level perspective, and not even just a technical perspective, but that program perspective on, what's it going to cost, how long is it going to take, things like that.
Yeah, awesome.
So that's it. Happy to just have a discussion or take any questions.
Yeah, I think that's cool. I think maybe I'll put you in the spotlight here. It'll be John Springmann time. Okay, yeah, I really appreciated that. I had a series of questions here lined up about kind of like the holistic design idea and what kind of factors you have to consider when you're thinking about it, but you just kind of banged them all out right there. So that's good. I like the idea that you talk about this, and from what I understand about design is that, yeah, you gave one kind of example here where you're looking at sensors and sensor power and et cetera. But I think this idea comes up with like every single design, when you're talking about creating a mechatronic system and you have to spec out a motor. Okay. Like I could just choose this huge friggin' motor and put it on there, and it's going to cost me some money, but at least I don't have to worry about, is it going to be powerful enough? Is it going to be, give me what I want? You just kind of go for the overkill and say, I'm not going to spend any time thinking about it. Or you say, all right, I really got to think about how much torque I need and, all these variables that go into it. That is just another one specific example, but this comes up all the time, like how large do you need to make the girders on this bridge? How large do you, it's every field, every almost design that you think about.
Yep.
And, we're hammering this home, even in this senior design that the students are sort of going through right now. They're on a limited time scale. So, you talk about in your presentation there that you have a trade-off between risk and schedule and cost. they're on this fixed schedule, so they got to do something else where maybe they accept more risk in their final prototype design. And then when they come present it to faculty, it doesn't work. That's a pretty big risk. But then they can say, well, we took a holistic engineering design approach and we're going to extend our schedule a little bit more. Maybe maybe that's their plan. So yeah, I really appreciated that view, and obviously really cool stuff that you work on is a nice example, but it's applicable in a lot of places, I think, which is cool.
Yeah.
I did want to take a few minutes to dive in on kind of your career. We've been going maybe about a half hour now, so I thought I would ask you a couple questions about that.
Sure.
We've had a lot of people on that have kind of gone the traditional role where you work for a company for a short amount of time, and you work for a company and you just get a paycheck, and your life is hunky dory, right? And that's kind of the way that it is. But you've kind of had this path where you worked for this company for a short time and then worked as a consultant. I wonder if you can just talk maybe a bit about what the benefits and drawbacks of sort of quote unquote being your own boss and being a consultant and everything that goes into sort of being a consultant. How is your dealings with a company different from a consultant perspective than as an employee perspective? So why don't we just start with that question first?
Yeah, sure. So I guess just a quick in general, consultant is a bit of a wide and loaded term. So kind of what consulting means from my perspective, or what I've been doing is, obviously fairly technical kind of engineering consultants, engineering work. Companies will hire me to either help them solve kind of a specific technical challenge that they're having, or help with things that they are not staffed up effectively to do. So consultants can be either brought in for their expertise, or just kind of surge support, and they say, hey, need help, but maybe don't have full-time employees. So quick perspectives. I mean, so I work independently. You are your own boss, and you kind of get out what you put into it. So it's, there's no micromanagement. It's kind of, self-motivated, figure out your own work, figure out your own schedule, things like that. One of the biggest differences is, you're typically hired on what's called a statement of work. So you're hired to do a specific job, you deliver that job, then you're paid for that job, either at the outcome or, some hourly rate or something. So it's much more of a transactional relationship, kind of exchange of goods, as opposed to employees. Consultants are typically brought in for their expertise, and they're independent. So one of the other main aspects is there's not the kind of career development or mentoring or coaching, right? As a company, your largest asset is arguably your employees, and there's, career ladders, there's mentoring, there's things like that. As a consultant, you're brought in because you're thought to be the expert in something already. So right. It's, something like my career development is something, I have to work with, I have mentors and things as well, but it's not the companies I'm working for. It's not my clients, right? It's kind of through my own network and things like that.
Do you take time out of what you would consider like your quote unquote working paid time to actually do some career development on your own?
I do in terms of like conferences and networking and that kind of stuff. Yeah.
Okay. Yeah. I think that's important. And that's something I never even really considered. Is they don't have a lot of investment in you if they're bringing you on as sort of like an assassin.
That's right. That's right.
So they're just saying, do what you do and what you're an expert at, and then move along.
That's
then
right.
We're done with you almost in a way.
That's right.
Do you feel that there's like some impersonal relationships that you get there, or feel like you have a colder relationship with those people? And is that maybe another drawback?
No, not necessarily. I think the relationship really just depends a lot more on. It's not defined by if you're a consultant or not. It's more just kind of how you engage, I think, with the customer, and there's a huge range. So I wouldn't say that's a for sure drawback. It can be. I think it kind of depends on the environment that you're looking for.
Yeah, sure.
There are like consultants. So I work independently, but there are consulting firms too, right? So there's companies that kind of provide consultants, but you are within a larger company as well. So
right. So as an independent consultant, you're kind of your own entity. How do you go about searching for people to work with? I mean, I know you're talking about networking and connections and things like that, but I would say that I don't know if you want to say that's a benefit or a drawback about like thinking you have to pursue your own clients and things like that. How do you go about that process of finding people who will hire you?
Yeah, so for me, I mean, so the small space industry is pretty niche and pretty small. So it is a lot about kind of networking and people that I worked with before, or references or recommendations. Companies will say, hey, I'm looking for someone to help with this, with this subject, and hopefully eventually they'll get to me. It's not through like a lot of advertising or anything like that. It's just kind of through networking and word of mouth.
Yeah,
but it's definitely a barrier to entry. I mean, I feel lucky to kind of be able to be successful and have continued business and stuff. It's a bit of a chicken and egg, kind of how do you start?
Yeah, right. Well, you started as an employee for a company that was doing a lot of this stuff, and then you eventually decided to sort of break away and sort of start your own thing. I'm curious what sort of sparked that, if you're willing to talk about that.
Oh yeah, for sure. I mean, I've always just kind of wanted to do my own thing and be my own boss. Just kind of a personal goal or personal interest. I will say too, the company I was working for, Black Sky, so it was a startup, right? I was actually the first engineer hired and the second employee of that company. And when you're in a startup company, as opposed to like a Boeing or a Lockheed or something like that, you're just exposed to a lot more, right? So I was exposed. Even if my job was technical, right? I was hired as an engineer, but with that, I was exposed to vendors, negotiating contracts, developing schedules, some legal aspects, working with licensing, things like that. Just because by nature of a small company, kind of everyone has to do everything. So I think because of that, it really kind of boosted my kind of network, and there's this whole ecosystem of startup companies that I got to know and things like that. So
that's cool. We have a question here from a student that says, how much time do you allocate towards networking and growing your business versus actually like executing the business?
Oh yeah, that's a good question. Ideally I'd be spending like 20% of my time, and kind of 80%, day-to-day work, and 20% really kind of growing the business. I probably don't spend quite that much, but I think it's kind of a target.
Do you feel like your work-life balance has shifted significantly since you kind of took the consulting role, or what's the story there?
Yeah, for me, it shifted, very much to the positive.
Okay.
Yeah.
Most people, when they think about running their own business or their own consulting thing, they think it's going to be tons of hours and blah, blah, blah. So can you expand on that a little bit?
Yeah. So that, again, kind of the type of consulting I'm doing, it's all based on hourly rates and kind of amount worked. As an independent consultant, you'll typically be able to charge more per hour than you will as like an employee. It's because companies have pretty significant overhead, and the cost of an employee to a company is much higher than your salary, right? Benefits, and company will charge a lot of overhead just for their ancillary functions like accounting and legal and things like that. So as a consultant, if you're independent, you can typically bill a lot more or make a lot more money per hour than you would as an employee. So that gives you the freedom to kind of work fewer hours. I'm not working I don't really work overtime or anything like that. Fewer hours, and be able to spend that time in business development and things like that.
That's good.
Yeah.
So with that idea, just so the students get a perspective, how do you handle healthcare, retirement, all those sorts of things, just from curiosity perspective?
Oh yeah. So I mean, retirement and that kind of stuff, I have 401ks set up, through my own company. That's just stuff that you have to kind of self-start, as opposed to being thrown into a big employee program.
Yeah.
And there's a lot of benefits actually to kind of sole proprietor 401ks and things like that. And then benefits, there's really two options. One is just through kind of the marketplace, per se, the federal marketplace for health plans. And then small companies in general, there are other companies that will pool small companies together to get kind of affordable health plans. So the reason that big companies can get reasonably priced healthcare is because of like volume, right? They're huge companies. Yeah. So there's other companies out there that will kind of pool small companies together and still be able to get that kind of benefits of volume. So, but yeah, all the administrative stuff like healthcare, retirement contracts, work that kind of on my own, and bring in other experts where needed, lawyers for contracts and things like that.
Yeah, I think this is particularly powerful too, because when you get assigned an engineering degree like these guys are getting, and then you go and you work in a field for a certain amount of time, you will hopefully become some miniature expert in a particular field. You know, you've gone this route and you've done this with small satellites and satellite mission planning and et cetera. And that makes you valuable and, employable for your skill set. So if you can find a niche and you can find maybe something that you become an expert in, this idea of becoming a consultant, even for students that are listening right now, is not so far-fetched, right?
Yeah.
I have a certain skill set in making composites where I could potentially maybe do some business. Like I'm a little bit of a coward, so I don't know if I could pull the trigger, but I don't think it would be so far-fetched if people wanted to sort of pursue this track after sort of becoming an expert in a very particular field. So would you say that it has generally like benefited your life, having this like freedom and this power? Yes.
Oh, definitely. But the other point I want to mention is that it's not no career is really needs to be a forever career. And I think, I had the mindset previously of like, you're looking for like the dream job and the thing you want to do forever. And if you can find that, like that's super ideal, but a job isn't indefinite. It isn't indefinite. You can change. So even for me with my consulting, like it's great for kind of my current season in life, but I do anticipate probably getting more of a traditional job at some point in the future. Like I said, kind of that there's pros and cons, kind of like career development, and just starting to work in other areas, other types of disciplines, other industries. Yeah. I'm planning a bit of a change of pace. But yeah, don't think of careers always as, kind of forever. You want to get experience in areas you're interested in, find things that you like, but you can always make moves.
Yeah, I think now more than ever that is true when it's so easy to understand that there are many jobs that exist and what those job openings are in a variety of areas. Because we're so connected with the internet, you can easily access the database of available jobs and potential careers. And so let's talk about this too, because I think this is interesting. I think a lot of people have some like loyalty to a company and working there for a long time. It's maybe like ingrained in their mentality.
Yeah.
And breaking away or looking for a different job seems a little unethical or unloyal. Do you have that feeling, and did you have like a drawback of going to a consultant from working for a company with any sort of like, I'm being disloyal by leaving them, or any of those ideas?
Yeah, I mean, not really on the loyalty front, but I was careful to kind of finish what I was working on.
Sure.
A tricky thing with leaving companies is you certainly don't want to burn any bridges,
right?
Because that can really hurt your ability to get jobs in the future. References are still a thing. So and also I do a lot of hiring for companies, and when you see resumes that people have kind of only been at locations for like a year at a time and then they change and they kind of just circle through these places, they're really not attractive to hire because companies see that and they're like, oh, this person's not going to stick around. But there's a valid middle ground. Like I don't think it's really a loyalty thing. It's do the job that you're asked to do, bring it to completion, and just I don't think leaving a company is disloyal. Companies realize that as well. There's, depending on career paths, there's certain things they can offer and not offer. And, startups versus the big companies are very different, for example. So you could kind of try them both out, things like that. So, yeah.
We have an interesting question from a student here who's curious about a level of aggression that you might take towards pursuing a client, or in the case of a student, maybe pursuing a job. So what's your take on, like pursuing a client and what level of aggression you might want, or if you're in the student's position that are listening here, how aggressively you might approach a job and maybe what some boundaries you might not want to cross?
Yeah, I mean, I think they're probably a bit different. I'm typically not that aggressive in pursuing clients. Like either they want my services or they don't. And I'll try to make it clear what the benefit would be for them to bring me on. But if they don't, then so be it. But I think for finding jobs, especially as students and new careers, it's a bit different. I don't know that I have any like hard rules for you, but it is a balance in terms of companies and recruiters do like to see demonstrated interest, right? So if you're applying a couple of times, or if you're emailing the recruiter, multiple times, that's okay. And it does demonstrate interest, especially if you can show, like, if you're writing an email and you really show like why you're interested in the position or the company, like, name some projects or something, or demonstrate that you've done more than just look at a job description, that you really kind of know the company and demonstrate your excitement. I think with that, kind of multiple messages to them can be helpful. But at a certain point, it comes off as desperate. So, because I don't know like what a hard rule of thumb is, but reach out kind of after you reach out 2 or 3 times. It's probably, and if you're not getting positive responses, then it's potentially time to try something else.
Yeah, gotcha. Okay, we're approaching 10:45 Central Time. I know you're in Seattle, so 8:45. He got up super early for you guys. You should be happy. I just maybe want to give you a floor if you want to say any last things about economic design or the job hiring process or consulting life or anything like that. Maybe just give you another second here if you want.
No, I don't think I really have anything else.
Okay, well, I guess with that then we'll close out, and I'll say again, John, thank you. It's cool to see the awesome satellites and space work and economic design, and also hear about the consulting life. So really appreciate it. Thanks for coming. That'll conclude the seminar. Thank you, students, for attending, and we'll see you next week. Actually, we will have a seminar next week. I'm going to actually give a lecture on geometric dimensioning and tolerancing. So next week we will have a seminar, more information on that to come. And thanks again, John.
Cool. Yep. See you, Kevin.
Yep. Bye-bye.